acid.
There we go. Okay. So this is an example of a titration curve problem where you are given all of the information about titration, namely the acid, the Ka value for the acid, the concentrations and volumes, and the point is to calculate the pH at the equivalence point. 3-chloropropanoic acid, we're just going to abbreviate that as HA. What do you think is the first thing to do?
Equation.
Write an equation. Very good. So HA plus OH minus reacts to form H2O plus A minus. Remember, this is not an equilibrium, or we assume that the equilibrium constant is very large. The titration reaction goes to depletion. What's the definition of the equivalence point?
pKa goes, no.
It's where the complete neutralization. It's also the stoichiometric point, when
The
the number of moles of the titrant is equal, of both substances is equivalent.
Very good. So why don't we begin by calculating the moles of acid that we're starting with. So the initial moles.
By the way, to give you a heads up, the approximation isn't valid in this case.
Oh, you're kidding.
You have to quadratic it out.
Crap. Oh well, that's what I get for making something up on the fly. Can you quadratic that for us?
Not yet.
Okay, thanks.
In that case.
So that's simply going to be the molarity times the volume is going to be 0.120 moles per liter times 0.0450 liters, or
0.0054 moles.
Can I have a third sig fig?
It's 0.
Okay, 0.00540 moles of HA. Now notice, because this is a one-to-one stoichiometry, that's also equal to the number of moles of hydroxide you need to add, and it's also equal to the number of moles of the conjugate base that will be present at the equivalence point. Okay? So, once we reach the equivalence point, so 0.00540 moles of HA is equal to 0.00540 moles of NaOH needed. So, once we reach the equivalence point, what is the main species present?
The conjugate base.
Very good. So at the equivalence point, once we have added as many moles of sodium hydroxide as we started with moles of acid, or as moles of acid we started with, the main equilibrium that's occurring is A minus plus H2O is in equilibrium with HA plus OH minus. Okay? So in order to calculate the pH, what do we have to calculate?
Well, one, we're going to need pKb.
Very good. This equilibrium is governed by Kb, and I can just write out the Kb expression. Kb is equal to the concentration of conjugate acid formed times the concentration of hydroxide divided by the concentration of A minus at the equivalence point, and this is going to be equal to 10 to the...
Oh, I see why it...
Yeah, because you have a
Yeah.
tiny concentration in a fairly...
Yeah.
Oh,
the
really?
concentration,
pKa.
you get a concentration of 0.0718 molar.
0.072, but yeah. 0.072.
All right, we get to that in a second.
Sorry.
Can you do the quadratic?
I'm
course?
doing it now.
Okay,
It
fine.
takes a bit.
All right, that's fine. Okay, so at the equivalence point, this is the main equilibrium that is being established, okay? And as a result of this, we're going to have a higher concentration of hydroxide than in pure water. We would expect the solution to be basic. So in order to solve for the pH, we need to calculate the hydroxide ion concentration, but in order to do that, we need to calculate the concentration of the conjugate base produced at the equivalence points. Okay? That then, so A minus at the equivalence point is equal to moles of A minus produced over volume. Well, we already said that the moles of A minus that we're producing is equal to the initial moles of HA.
Ah, dang. I messed up.
Don't
Sorry.
quadratic it out, just put it in your calculator, come on.
No, I messed
Over,
Sorry, I missed some... Wait, no. I may be wrong. The quadratic might work.
over the
'Cause I
total
plugged
volume.
I plugged in Ka rather than Kb. I need to calculate Kb.
I hate it when I do that. Over the total volume, which is not just the volume of solution we started with, but the volume of base we needed to reach the equivalence point. So what do we have to calculate? The volume of base needed to reach the equivalence point in order to figure out the total
Cool, I
volume.
think it works.
Yeah, probably
Okay.
it does.
It works.
All right. So the volume of sodium hydroxide solution needed is simply equal to the moles of sodium hydroxide needed, which we said are equal to the initial moles of HA, 0.00540,
Oh yeah, this is going to be fun.
divided by the concentration of hydroxide, which is 0.175 molar, or
It's going to be 0.0718 or 0.0720 if you take Cole's number.
the total volume. No, because I'm calculating the volume of sodium hydroxide needed. So that's
Oh.
that's
30.857.
0.0309 liters or 30.9 milliliters.
Yeah.
So
Approximation works.
so that lets us calculate A minus as 0.00540 moles of A minus produced divided by the sum of the initial volume of acid, which is 0.0450 liters, plus the volume of sodium hydroxide required to reach the equivalence point, 0.0309 liters, or
0.072 or 0.0718.
0.0718 molar is the concentration of A minus. Great. Now we can go back and we can plug that into, let's hope this is not too annoying, plug this into my Kb expression in order to find the hydroxide ion concentration. So Kb equals x squared over 0.0718 minus x is going to be equal to the Kb value. Are you sure the approximation is not going to work?
No, it works. It works.
We figured
it
it out.
works.
It's
Oh,
Cole
okay,
confused.
okay.
I put in
Ka instead of Kb.
yeah.
Okay.
If you KB is much smaller than Ka, so if you put
Right,
it
so
in,
it's 10,
approximation is
10 to the negative 10.02,
Yeah.
which is 9.5 times 10 to the negative 11. Oh, sweet. Okay. 9.5 times 10 to the negative 11, which we got again as Kw over Ka. So now x is the hydroxide ion concentration. It's the square root of 0.0718 times 9.5 times 10 to the negative 11 is equal to 2.6 times 10 to the negative 6th.
Yep.
And
People in
using the
intermediate steps.
Barrett simplification, pH equals 14.00 plus the logarithm of 2.6 times 10 to the negative 6th, or 8.42.
Yes.
Ta-da.
I misread that.
Which is consistent. It is greater than 7 at the equivalence point when you're titrating a weak acid with a strong base. You are generating a solution of the conjugate base. The conjugate base of a weak acid is a stronger base than water, so you would predict that the pH would be greater than 7, and in fact, you do. Can I get a huzzah?
Huzzah!
Bye.
You didn't stop it.
I didn't. Oh.